Hello everyone, welcome to We Civil Engineers. Imagine you arrive at a construction site and the slab settling is complete. Steel bars are laying everywhere and workers are asking, Sir, how many bars should we cut? What length? How much steel is required? Now, if there is no proper bar bending schedule, steel gets wasted and cutting becomes wrong and project cost increases significantly. That's why every civil engineer must understand BBS. Today we are going to learn one of the most important topic in structural detailing, that is bar bending schedule of slab. And it is not just a theory. We will calculate cutting length of main bar, distribution bar, number of bars required for the slab, hook length and bend deduction, and we will see total steel quantity required for a particular slab. Exactly like a real site engineer. Let us first understand the slab geometry. So we have a slab with 11-meter length and 5.5 meter breadth. So this is a two-way slab. Here we are using main bar of 16 mm diameter and distribution bar of 12 mm diameter. Distribution bars are placed at 200 mm center to center spacing and main bars are placed at 100 mm center to center spacing. So this is the given data which we have currently with us. Length is 11 meter, breadth is 5.5 meter, main bar diameter is 16 mm, distribution bar diameter is 12 mm, main bar spaced at 100 mm and distribution bars are spaced at 200 mm. So here is the important concept. Main bar resists the major bending tension. So they are placed along the shorter direction. And distribution bar distributes the loads and controls the shrinkage cracks. So they are placed perpendicular to main bars. A common mistake beginners make is confusing between bar direction. So remember this simple rule. Main bars always go in shorter direction. Now let's calculate the cutting length of main bar. This is where many interview question comes from. The formula of cutting length of main bar is L plus 10D plus 10D minus 2 times of 2D. Here L is clear span length, 10D is hook length at each end, 2D is bend deduction at each end. Let us substitute the value to get the cutting length of main bar. Bend deduction is 2D. Here D is diameter of main bar. 2 multiplied by 16 equals to 32 mm, which is equals to 0.032 meter. Hook length is 10D. 10 multiplied by 16, which is equals to 160 mm. And if you convert it to meter, then it will come as 0.160 meter. So let's substitute these values to get the cutting length of main bar. So the total length of main bar is 5.5 meter plus 0.160 plus 0.160 minus 2 times of 0.032, and if you calculate it, then it will come as 5.756 meter. So the cutting length of one main bar is 5.756 meter. This is exact length worker should cut on site. Now some students might ask, Sir, why are we subtracting bend deduction? Excellent question. When steel bends, part of bend already consumed length internally. Hence we deduct it. If we ignore bend deduction, the bar becomes longer, spacing gets disturbed, concrete cover reduces, and reinforcement become inaccurate. This small deduction may look tiny, but imagine 100 or 200 bars. Even a small error creates huge steel wastage. That's why professional quantity surveyor and site engineer never ignore bend deduction. Cutting length of distribution bar. The formula for cutting length of distribution bar is L plus 9D plus 9D minus 2 times of 2D. Let's substitute the value to get the hook length. 9 multiplied by 12. 12 is distribution bar diameter, which is equals to 108 mm. And if you convert it to meters, then it will come as 0.108 meter. Bend deduction. 2 times of diameter, which is 24 mm. And if you convert it to meters, then 0.024 m, and here span is 11 meters. So substitute these three values to get the total length of distribution bar. 11 plus 0.108 plus 0.108 minus 2 times of 0.024, which is equals to 11.168 meter. So the cutting length of one distribution bar is 11.168 meters. Now let us calculate the number of bars required. This is another very important site calculation. The formula for calculating number of bar is span divided by spacing plus 1. So let's calculate the number of main bars required. So the span is 11 meter and the spacing between the main bar is 100 mm, which is 0.1 meter. So divide span by spacing 11 meter by 0.1 meter, which is equals to 110 bars. And the formula for number of bars is span by spacing plus 1. Add 1 bar to it, then you will get the total main bars required for this slab. So 110 plus 1, which is equals to 111. So we require 111 main bars. Same formula for calculating distribution bar. Number of bars equals to span by spacing plus 1. So here the span or breadth is 5.5 meter and the spacing between two distribution bar is 200 mm, which is 0.2 meters. So divide 5.5 meter by 0.2 meters, then you will get the value of 27.5. So remember we have to add plus 1 to get the total number of bars. So add plus 1 to it and the total number of bars is 28.5. So and if you round it off, then the total number of bars comes as 29 numbers. So the total distribution bars are 29 numbers. Have you noticed something interesting here? The number of main bars are much more higher than the distribution bar because the spacing between the main bars is less than distribution bar and it is placed along the longer span of the slab. Now think like a site engineer. Why main bars are placed closely? Because they carry major tension forces, they resist bending, and slab usually fails in tension first. That's why the main bar diameters are larger and they are placed closely and the quantity is more. And these bars are used as main reinforcement. Let us prepare the final BBS summary table. So bar type is distribution bar and diameter of distribution bar is 12 mm and cutting length which we have derived from the formula is 11.168 meters and total number of bars are 29 numbers. So if you multiply these two values, then you will get the total cutting length for the slab. So for the slab, you will need 323.87 meters of distribution bar. And for the main bar, the diameter is 16 mm, cutting length is 5.756 meter, and the number of bars are 111 numbers. And the spacing between them is 100 mm. So multiply number of bars with cutting length, then you will get the total length required for main bar. So for this slab, you will need 638.92 meter length of main bar. Now let me ask you some common interview questions. Question 1. Why do we add plus 1 in bar calculation? The answer is because the first bar also occupies the space. Question number 2. Why are hooks provided? The hooks are provided to improve the anchorage and the bond between steel and concrete. Question number 3. Why are main bars placed in shorter span? I have already explained you because shorter span experiences high bending moments. That's why main bars are placed in shorter span. Question number 4. What happens if bending deduction ignored? If bending deduction ignored, then steel quantity increases incorrectly and reinforcements placement becomes inaccurate and this causes congestion in the steel bars and the cost of the steel might go significantly higher. In these lessons, you have learned that main bars resist tension, distribution bars control cracking, and cutting length of bar includes hook length and bend deductions. Number of bar formula is extremely important. Small calculation mistake create major steel wastage, and BBS is essential for execution, billing and planning. And most importantly, a good civil engineer does not draw reinforcement. He understands why it is provided, how it behaves, and how to execute it accurately on site. This is what makes someone a professional engineer. If this lecture helped you understand BBS practically, then start practicing with different slab size yourself, because the more BBS problems you solve, the stronger your site knowledge becomes. And remember, structural drawing shows design and BBS converts design into execution. So thank you for watching. If you like this lecture, then please like, share and subscribe to our channel, We Civil Engineers. Thank you.